exploiting EDCA for feedback channels in hybrid VLC Wi-Fi architectures. Abstract. In this paper, we consider integrated VLC and Wi-Fi technologies in scenario in which light-emitting diodes (LEDs) acting as network access point (APs) for ultra-dense Internet of Things applications are deployed into an indoor lighting infrastructure. In such scenario, RF links can be exploited for complementing VLC links in dealing with mobility and bidirectional communications, which can be problematic due to the limited coverage areas and self-generated interference of VLC APs. In particular, we consider the possibility of supporting a technology-based duplexing scheme in which download and uplink transmissions are performed by means, respectively, of VLC and Wi-Fi interface integrated into the same node. In order to fully exploit the VLC bandwidth in the presence of background Wi-Fi traffic and multiple coexisting VLC links, we discussed the importance of adopting a periodization mechanism based on EDCA, as well as frame aggregation for the uplink channels of integrated architecture. Our considerations are corroborated by numerical results based on NS simulator and a real simple experiment. Index terms: visible light communications, radio frequency, hybrid architecture, EDCA, Open VLC. Introduction. In the last years, we have assisted to an impressive growth of capacity demand for wireless networks due to the proliferation of portable user devices and smart objects connected to the Internet. According to a recent Cisco report, mobile data traffic will account for 71% of Internet protocol traffic by 2022, in which more than 80% of mobile data traffic is generated in indoor spaces. The rising demand for capacity, especially in indoor scenarios, overrode conventional RF-based technologies. Therefore, technologies working on advanced spectrum sharing solutions 2 and 3, or innovative spectrum portions such as millimeter waves, and visible light communications (VLCs) have been proposed as proposed solutions. Among these, the VLC technology is a very promising alternative, explicitly considered in the design of 5G systems 4 and 5, because it offers a high bandwidth immunity to interference from electromagnetic sources and many possible for special use. The uptaking of VLC communication is also due to the widespread adoption of light-emitting diode (LEDs) for illuminations. LED light have several advantages compared with traditional incandescent lamps, such as 75% reduction of power consumption and 2,500% increase in lifespan. 6. The market share of LED light is expected to rise with an annual growth rate of 13.4% from 2020 to 2027. Exploiting the LED deployed for illumination in order to modulate a light signal and transmitting data is an exciting opportunity. However, the design of the integrated illumination and data distribution infrastructure requires to solve some problems. The limited coverage area of VLC links, which enable high-density spatial use, has a counter effect of making node mobility management difficult. Another difficulty is due to the support of uplink channels, because the light emitted for illumination purposes represents a high-power interference source for uplink signals. For this reason, uplink channels can be implemented by working on different spectrum portions, such as infrared signals 7, RF signals 8. Hybrid VLC and radio frequency RF systems have been proposed as state-of-the-art solutions to solve both the coverage and uplink transmission problems 9 to 11. Several previous studies have applied hybrid VLC to RF connectivity scheme to improve the performance of both technologies 12 to 14. In 9, omnidirectional RF links is integrated to multiple directional VLC links for optimizing the downlink capacity under different network scenarios. A scenario architecture is analyzed in 15, where the author also focused on per-user rate performance. In general, the radio links is used as backup channel in case of VLC coverage holes or as a feedback channels for VLC data and control information aids. For example, for sending signal strength reports to the transmitter. In this paper, we focused on the limits of VLC Wi-Fi integrated architectures. In particular, we consider the possibility of supporting a technology-based duplexing scheme in which downlink and uplink transmissions are performed separately on the VLC and Wi-Fi interface is deployed on the same node. Since Wi-Fi links have a much wider coverage area than VLC ones, in the presence of high-density VLC links or other background Wi-Fi traffic, the Wi-Fi network may be congested. Congestion of the Wi-Fi networks in turn has an impact on the performance of the VLC links. More into detail, we consider a scenario in which VLC links are used for reliable data transfer towards smart objects. We assume a congestion control transport protocol such as TCP is used for data transfers, which is assumption TCP acknowledgement are sent in uplink on Wi-Fi networks and can result in a bottleneck for the whole integrated system. We then discuss some possible solutions for increasing the network capacity available for the Wi-Fi feedback channels of the VLC node. The benefits of the proposed approach are shown by means of NS3 simulator and simple experiment. The remainder of this paper is organized as follows. In section 2, we present our reference network scenario and some motivations for our work. In section 3, we discuss how the design of an integrated VLC Wi-Fi system creates some coupling effects between the performance perceived in both the VLC and Wi-Fi network segment. We also introduce the channel access mechanisms which can be exploited for providing a feedback channels to VLC communications. Section 4 provides numerical result obtaining using NS3 simulations and some preliminary experimental tests. Finally, conclusions are drawn in section 5. Scenario and motivations. This section describes our reference scenarios for a hybrid VLC Wi-Fi networks architecture and scalability issue due to the usage of Wi-Fi technology for implementing the uplink feedback channels. Hybrid VLC Wi-Fi network architecture. We assume that integrated VLC Wi-Fi network is available in an indoor space, where VLC access points are embedded into ceiling lamps and of the illumination infrastructure and connected, together with Wi-Fi access points to a local area network. Therefore, the indoor space is covered by multiple access points employing both the VLC and Wi-Fi technology for supporting high-density terminal node. The configuration of each AP in terms of physical and access layer parameters, as well as configuration of the internal routes, are decided by the centralized controller called Intelligent Control Unit. In a similar fashion to one reported in 9, we assume that each VLC receiver also features a Wi-Fi device, which is used for uplink transmissions. In case the VLC receivers are downloading data from the VLC APs, the common Wi-Fi infrastructure provides feedback channels for the VLC connections. The Intelligent Control Unit is a central controller where all the decisions about network configurations are taken based on network conditions and other variable channel factors. Indeed, network performances can be optimized by opportunistically adapting the Wi-Fi contention parameters and operating channels as a function of network load. Moreover, the usage of the central controller simplifies the mobility management, while setting nodes can exploit by the high bandwidth VLC links for downloading data. Highly dynamic nodes can be switched to the Wi-Fi network to avoid service interruptions due to frequent handovers. Figure 1 shows a schematic view of our reference network architecture. For simplistically, we assume that each ramps available of the for the illumination infrastructure is serving one mobile node. Each VLC link is unidirectional from the VLC AP to a mobile node, also called the VLC receiver, and it is labeled with a progressive identifier. No interference is generated between one VLC links and its neighbors. VLC receivers perform uplink transmissions toward the network infrastructure by means of the Wi-Fi interface. A single Wi-Fi access point figure the throughput of our real VLC links using the OpenVLC open source platform. When TCP acknowledgements are sent on Wi-Fi networks with a varying number of contending nodes, covers the whole environment where other single interface Wi-Fi node may be present. B. Congestion impact on inter-technology performance. In our reference scenario, mobile nodes receive and transmit data by means of two different technologies, thus introducing some coupling effects between the performance of coexisting VLC and Wi-Fi networks. In particular, it is evident that uplink Wi-Fi transmissions performed by neighbor mobile nodes may interfere with each other, while downlink VLC transmissions are orthogonal. Since most applications generate bidirectional traffic flows, even when the dominant flow is in the downlink, it is important to understand in which conditions the Wi-Fi network can act as bottleneck for the whole system. In particular, we consider the case in which mobile nodes are involved in a file download from the network. By using the TCP transport protocol, all the TCP acknowledgement generated by each VLC links contains in the same Wi-Fi network. Therefore, the number of coexisting VLC links cannot be arbitrarily large, because the delays and losses of TCP acknowledgement will force VLC transmitters to reduce their transmission rate. Moreover, in presence of background Wi-Fi traffic, the rate reduction due to TCP congestion control can occur even in presence of a single VLC links. In order to demonstrate the impact of such phenomenon, we ran a simple experiment in our lab of University of Fernamo by using the OpenVLC platform for implementing the VLC links. OpenVLC is an open source, flexible, and low-cost VLC system 16 developed for testing innovative protocols exploiting the VLC technology. We implemented our mobile nodes on Bingle-Born Black (BBB) used as the embedded computer running the VLC access protocol and integrating a visible light TX-RX front-end. The details on the hardware and software architecture are presented in 16. We also integrated a Wi-Fi interface on the same Bingle-Born and configured the routing rules needed to send up the uplink data through the Wi-Fi interface. Although the OpenVLC interface can achieve a maximum throughput 400 kbps, much lower than state-of-the-art VLC data rates, we were able to reproduce the above-mentioned phenomenon by tuning the Wi-Fi data rate to a fixed value of 6 Mbps. In Figure 2, the blue lines shows the TCP throughput of the OpenVLC links configured between one node acting as VLC access point and one node acting as a mobile node, when the number of coexisting Wi-Fi nodes varies from 0 to 5. VLC packets have fixed size of 1,500 bytes. Each coexisting Wi-Fi node generates an UDP traffic flow toward the common Wi-Fi access point at a source rate of 800 kbps. Packets are transmitted with a physical transmission rate of 6 Mbps. From the figure, we can observe that when no coexisting Wi-Fi node is active, the VLC links achieved a maximum rate slightly lower than 400 kbps. As the congestion level on the Wi-Fi network increases due to the activation of multiple Wi-Fi nodes, such as throughput progressively reduced down to almost zero when 5 nodes are active. This happened despite the fact that the uplink traffic flow generated by the VLC receiver has a maximum rate of about 10 kbps by considering that each TCP data frame will generate one acknowledgement, whose size is 40 bytes only. The figure also reports observed minimum and maximum values for our experimental result. Observed when repeating the experiment 5 times. The red line in figure 2 shows the performance achieved when the TCP X are transmitted with the priority mechanisms, as described in the following section. Increasing capacity of VLC feedback channels. This section presents some possible solutions for avoiding that the Wi-Fi network will act as bottleneck for multiple orthogonal VLC links. The idea is exploiting the EDCA access categories to prioritize the uplink data traffic generated by the VLC links, as well as frame aggregation for sending multiple TCP acknowledgement in a single channel access. A priority on channel access and the frame aggregation. In order to arbitrate the access the shared wireless medium, Wi-Fi nodes employ a random access mechanism based on the well-known EDCA protocol. Stations with frames to transmit starter carrier sense procedure and check whether the channel is available or busy. If the channel is sensed an ideal for the arbitration interframe spaces AIFS interval, which depends on the access category of the pending frame. Stations can transmit. Otherwise, a random bag-off counter is extracted in a range called convention window, whose minimum CW minimum and maximum CW max values also depends on accessory category. The bag-off counter is decremented when the channel is ideal and frozen when it is busy. Until it reaches a value equal to 0, only this time the station can attempt the channel transmission. Contention windows are doubled when transmission attempts fails up to the maximum value, and reset to the minimum value in case of success. Therefore, the probability to access the channel depends on the AIFS interval and on coverage contention window, because both the parameters affect the time required for resetting the bag-off counter to 0. 4 different access categories called background became best effort video call and voice are defined EDCA for giving different channel shares to traffic flows with heterogeneous requirement. The high priority classes EDCA and EDCA have difficult AIFS values set to 2 bag-off slots. Moreover, they use small contention windows, CW mean equal to 3 and 7, CW max equal to 7 and 15 respectively. For EDCA and for EDCA, both of the low priority classes use CW mean 15 and CW max 1023. Best effort flows employ an AIFS value of 3 bag-off slots, which background flows adopt an AIFS values of 7 bag-off slots. Once a station wins the contention and obtains a channel access grant, it can hold the channel for time interval called transmission opportunity (TXOP). In case the duration of the transmission opportunity exceeds our frame transmission time, multiple frames can be transmitted in the same channel access, with the possibility of using per frame or cumulate acknowledgement. This mechanism allows to improve the channel utilization efficiency and to equalize the channel holding times of stations employing heterogeneous data rate or frame sizes. Another mechanism introduced for improving the channel utilization efficiency in IEEE 802.11 and 802.11 AC In the usage of frame aggregation, multiple service data units sent by upper layers can be packed up to a maximum size are transmitted as a single frame, 17 to 19. This mechanism is suitable for the transmission of TCP acknowledgement, which are small in size and lead to significant main layer overhead when transmitted as independent frames. EDCA mapping TCP on ACVA. We propose to exploit EDCA periodization mechanisms for the transmission TCP acknowledgement generated by the VLC links. In particular, we propose to map these traffic flows to priority classes, ECVI to main regions. First, reducing the access delays for TCPX and therefore the round-trip time of the TCP links. In order to fully exploit the capacity available on the VLC links, enabling burst transmission of multiple TCP acknowledgement within the ECVI transmission opportunity, whose default value is set to 3.01 millisecond, thus reducing the number of contention required by VLC node. Indeed, although the bandwidth required by the TCPX is a small fraction of the downlink VLC rate, the random access protocol or Wi-Fi networks cannot guarantee the allocation of the bandwidth. For analyzing possibility of allocating the bandwidth required by the TCPX, it is important to qualify the maximum possible channels share width can be allocated to a VLC node when they are permanently in a contention state. Obviously, the capacity demand of TCPX is lower than the maximum possible share. Other flows can grab the exceeding resources. Consider the case in which each station has a single contention flow. Let M be the number of Wi-Fi background nodes. For example, grid node requiring the maximum possible capacity, coexisting with the MVLC receivers demanding kbps, s kilobps of the Wi-Fi network. These flows are originated by the TCP acknowledgement of the VLC links, and therefore S is proportional to the VLC link's capacity. The total capacity C available on the Wi-Fi network depends on the total number of contending stations, which affect the amount of resources wasted because of the channel ideal intervals and collisions. Second, the channel holdings times T Wi-Fi and T VLC experienced respectively by background Wi-Fi node and VLC node. The maximum channel share XVLC available for each VLC node is given by T VLC m.T Wi-Fi plus n.T VLC, which can be very penalized in case each TCP is transmitted in independent contentions. For example, when T VLC is much smaller than T Wi-Fi, whenever XVLC upper S in principle, the TCPX flow can be accommodated into the network. However, because of TCP congested control, the ECK flows rate can be reduced to a value smaller than S. Because of the delay jitter observed in the Wi-Fi access network, a priority scheme can be adopted for increasing the maximum share allocated to VLC node. Basically, if K is a ratio between the minimum contention window of background Wi-Fi nodes and VLC receivers, the weight of the background Wi-Fi nodes for delivering the VLC maximum shares is approximately reducing by the factor equal to K. For example, XVLC, TVLC, MK, Wi-Fi, and TVLC. The capacity share of Wi-Fi background nodes can be further reduced by increasing the AIFS value in comparison to one used by VLC receivers. By assuming that the background Wi-Fi node employ the best default access category, we propose to adopt the ACVI access priority for ensuring a good channel shares to the TCPX generated by VLC receivers. Indeed, HVI employs a smaller contention windows and AIFS values in comparison to HVE BE value, and transmission opportunity set to 3.01 millisecond, which makes possible the transmission of multiple TCP/X frames in the channel access attempt. We call EDCA such a prioritization mechanism applied to the transmission TCP/X. Numerical result. In this section, we evaluate the performance of the integrated VLC Wi-Fi networks to see the impact of background Wi-Fi node on VLC performance with and without EDCA or frame aggregation. Simulation platform and setup. We use NS3 simulating our hybrid VLC Wi-Fi networks. NS3 is widely adopted for simulating for the performance of large-scale networks. Moreover, it provides an extensive library with many standard networks protocols and local access technologies, and an easy interface for defining the network topology. The configuration of each network node requires installation of protocol stacks and can mimic every aspect of real nodes. Several tools are included in the simulator for visualizing the behavior on the networks, debugging through analyzing of event log, and collecting results for performance evaluation. Figure 3 summarizes the simulation scenario created in NS3. There are two types of nodes in the simulation. Nodes employing only a single Wi-Fi interface STA1 to STA-M, and nodes integrated one Wi-Fi and one VLC interface, VLC1 to VLC-N, also called the VLC node. The first group of nodes will act as background traffic for studying the impact of Wi-Fi congestion on the VLC links. Since NS3's lacking support for high-speed VLC simulation, we also employed Wi-Fi links in order to emulate those. Specifically, we configured IEEE 802.11ac orthogonal channels, 11ac orthogonal channels with fixed VHF-MCS with a maximum measured throughput of 60 Mbps. The shared Wi-Fi networks configured in infrastructure mode with QoS support and physical layer based on 802.11a configured with a fixed data rate of 6 Mbps. The reason for choosing a low data rate for the Wi-Fi networks guaranteeing that VLC data rates are one order of magnitude greater than Wi-Fi ones, as expected in the current state of art solutions. As different skills, the VLC emulating access points were placed close to their respective mobile node, with no mobility model in Figure 3 simulation scenarios with several background nodes in the network. This simulation, in order to guarantee high-quality channel conditions, furthermore, all the STA are placed at the same distance from AP. Emulation of the simple links was carried out by setting up static routes on the mobile nodes so that the uplink data is forwarded through the common Wi-Fi network. Regarding the contention parameters, we configured the background nodes as belonging to access category HVC, while VLC nodes employ HVE BE without frame aggregation, or HVI, in different simulation scenarios. Other configuration parameters are listed in Table 1. B. Performance analysis of the VLC Wi-Fi integrated network. As a first simulation scenario, we considered a network topology similar to our simple experiment, with one VLC links and several greedy Wi-Fi nodes in background. The downlink source rate of the VLC node is configured at 10 Mbps, which is higher than the maximum rate currently supported by the OpenVLC prototype, and the maximum downlink rate with a segment size equal to 1,500 bytes. The uplink traffic flows to TCP/ACK was measured be approximately 190 kbps. Figure 4 shows the downlink throughput result, solid lines obtained by the reference VLC nodes. As the number of background Wi-Fi nodes M increased from 0 to 10, and under the different options for contention protocol, we use the flow monitor function in NS3, computes the throughput of the hybrid VLC Wi-Fi traffic flows at the network layer, for example, including the header overhead. When the TCP/ACKs are sent by using the same ACK BE access category of the Wi-Fi background nodes, blue line. Comparison of the VLC downlinks, solid, Wi-Fi uplink, dashed, throughput for N1, hybrid VLC Wi-Fi station. Without frame aggregation, the source rate of the VLC links cannot be sustained. One active Wi-Fi background node is enough for observing a throughput reduction. It will also give a look to the uplink throughput dashed lines y-axis scaling indicated on the right. We see the sudden reduction to 80 kbps with the number of background stations M equal to 1. Indeed, being TCP/ACK is small in size, the channel shares available for the VLC node is not enough for allocating a flow of 190 kbps. As a consequence, the TCP congestion controls react by reducing the transmission rate on the VLC links. In case we activate the frame aggregation option, green solid line, VLC links are available to work at the maximum rate up to number of background stations M equal 5. This happens despite the fact of the uplink throughput, green dashed line, is slightly lower than 190 kbps, thanks to the possibility of exploiting cumulate ACK for tolerating some ACK losses. Finally, we set the ACK VI priority for the TCP/ACKs, red solid line. The reference VLC links works well up to M equal 10 background nodes. For this access mode, we also observe that the uplink throughput dash line is available to guarantee a rate of about 140 kbps for transmitting TCP/ACKs when M is ranging 5 to 10. Note that the number of TCP/ACKs is when can be accommodated in a single transmission opportunity with default HVM settings is equal to 15, which is smaller than the number of TCP/ACKs which can be aggregated in a max service data unit MSDU of 1500 bytes. Therefore, the sustainability of the VLC downlink throughput is not only due to the improvement on channel utilization, but also on the channel access prioritization mechanism. Reducing the access delays and delays jitter improves TCP performance. Figure 5 shows the throughput result of our reference VLC node. In a simulation scenarios in which total number n equal 4 of VLC links are active, together with a variable number m of Wi-Fi background nodes, again we consider the 3 different access nodes using the same access category of background Wi-Fi nodes, blue curves, activating frame aggregation, green curves, exploiting EDCA prioritization, red curves. The behavior of the curves are similar to the previous scenarios, although in such a case multiple TCP/ACK flows are contained simultaneously. Priority HVI flows can be particularly sensitive to collisions in case of congestion generated by the same access category because of the small contention with values used in contention. However, Figure 5 comparison of the VLC links solid Wi-Fi uplink dashes throughput for M4 hybrid VLC Wi-Fi stations. Want remarks that the rate of each uplink flow is a small percentage of the VLC link's capacity, and therefore the Wi-Fi networks can accommodate several coexisting VLC links before the saturating. Indeed, for m equals 0, our reference VLC links works at the maximum rate without using prioritization. As the number of m of background node increases, the slope degradation is more evident for the case in which TCP-X are transmitted using the frame aggregation, while the usage of prioritization only leads a slope reduction of about 4% for the worst congestion case m equals 10. Figure 6 shows the end-to-end average delays of the TCP-X flows measured under the 3 different access modes considered in our study, and for both the scenarios of the single VLC links, solid line, and 4 VLC links, dashed lines. When TCP-X are mapped to the ACVE access category, blue and green lines, we observe that the increased congestion level due to VLC links has a minimal impact on the average delays. For example, dashed and solid lines almost coincide. Conversely, when the TCP-X flows are mapped to the ACVI access category, the performance degrade in presence of the competing high priority flows, dashed red line. However, the prioritization mechanism also allows to achieve access delays which are one order of magnitude smaller than the one achieved when using ACVE and frame aggregation red curves vs green curves. Figure 7 shows throughput achieved by the Wi-Fi background nodes in both scenarios of single VLC links. Background STA overall throughput, solid line and 4 VLC links dashed line as expected. The throughput reduction for Wi-Fi background node is more evident in case of the VLC links employed prioritization mechanism red curves, especially when multiple priority flows are active dashed red curves. Summarizing our simulation results shows that EDCA provides standard compliant, reliable systems, which improves the performance of the hybrid system we simulated. In order to better support our result, we added EDCA ACVI priority class on the Wi-Fi devices used by the VLC return channel in the open VLC experiment reported in Figure 2. The measured throughput is presented by the orange line in the figure, which shows how the system throughput exhibits a significant improvement. Conclusions. In this paper, we have discussed how the random access protocol employed in Wi-Fi networks can impair a hybrid VLC Wi-Fi communication system. Indeed, in case of congestion, channel access delays can suffer significant jitters, while the transmission of small feedback frames, such as the TCP-X, can significantly reduce the overall network capacity. To cope with these limitations, we analyze the impact of different options available at the MAC layer on the performance of the VLC links and Wi-Fi node. Although the random nature of the Wi-Fi access mechanisms does not allow to guarantee fixed channels shared to VLC feedback channels, several optimizations are possible. On one side, using frame aggregation at the max service level, or enabling transmission of TCP frames in bursts within a single transmission opportunity, allows a dramatic reduction on the number of contentions required by the feedback traffic flows and an improvement of the channel utilization efficiency. On the other side, using the prioritization mechanism for TCP-X is important for optimizing the behavior of the TCP transport protocol and therefore fully utilize the VLC downlinks. We qualified the performance benefit which can be achieved on the VLC network segment by using different options on the access protocol employed in the Wi-Fi network segment in the several simulation scenarios and the simple small-scale experiment. Further investigation will involve the generalization of these results when both VLC and Wi-Fi network segment employ state-of-the-art data rate, as well as the analysis of solutions for allocating VLC feedback channels in presence of node mobility, competing high priority flows, and multiple coexisting Wi-Fi network. Acknowledgement. This has been funded by the European Union's Horizon 2020 Research and Innovation Program under the Marie-Curie Grant Agreement Enlightenment